I wanted to start by going over the formulas for some of the measures of dispersion we talked about in the last video. I wanted to go over the formulas for population and sample variance and for population and sample standard deviation. These formulas use the symbols that we went over in the last video. So I'll remind you what the symbols stand for. This is the formula for a population variance. It's x minus mu, this Greek symbol that looks sort of like a U. It's actually the sum of that squared over capital N. Now what is this formula saying? The x minus mu means a data value minus the population mean. Remember that this mu symbol right here stands for the mean of a population. So what this formula is saying is to subtract each data value, each x, by the population mean, and then square the answer. So that's the step that we did when we subtracted each value by the mean and we squared all the answers. This right here is a summation symbol. What it's saying is for us to add all of the squared answers. And when we calculated the population variance in the last video, one of the steps that we did was adding all of the squared answers. What this n on the bottom is saying is to divide the total of the squared deviations by the population size, by the number of people in the population. The capital N stands for the number of people in the population. So when we divide the total of the squared deviations, which we have on top, by the population size on the bottom, we get the average or the mean of the squared deviations, which is the population variance. Let's now talk about the formula for the sample variance. It's a similar formula, but some of the symbols are a little bit different. X still means an individual data value. It's x minus x bar squared over lowercase n. So notice how this symbol has changed to an x bar, and this symbol right here, this uppercase n, has changed to a lowercase n. Now why has it changed? Well, x bar is a symbol for a sample mean. When you calculate a sample variance, you're subtracting each data value by the sample mean, by the mean of the sample. So the mean is an x bar instead of a mu. And when you calculate a sample variance, you're dividing the total of the squared deviations, which is up here, by the number of people in the sample. Actually, I'm sorry, you don't divide it by the number of people in the sample. You divide it by the number of people in the sample minus 1, because the sample variance has an adjusted formula in which you don't divide by the number of people in the sample, you divide by 1 less than the number of people in the sample. So this formula is telling us to subtract each data value by the sample mean and square the answer, square each of the answers, and then add all of the squared answers, and then divide the total that you get on top by 1 less than the number of people in the sample. Remember, lowercase n is the number of people in the sample, and 1 less than that number is n minus 1. Now what about the formula for population standard deviation? I'm sorry, I should have said population variance and no, actually, I did write it out correctly. Sorry. I thought I made a mistake, but I didn't. Remember that the population standard deviation is just the square root of the population variance. If you take the variance and go one step further and get the square root, you get the standard deviation. So, to get the formula for the population standard deviation, we just take the variance formula, we take the population variance formula, and put it under the square root sign, like this. So if we take the population variance formula and put it under the square root sign, we get the formula for population standard deviation. What about the formula for sample standard deviation? Well, the sample standard deviation is the square root of the sample variance. So we just take the sample variance formula and put it under the square root sign. And there's our formula. What this formula is saying is that if you want the sample standard deviation, just take the sample variance and find the square root of the sample variance, and that equals the sample standard deviation. What you have to do to get the sample standard deviation is use this formula to calculate the sample variance, and then go one step further and get the square root of the sample variance. And these are the four formulas that I wanted to cover. Next, I wanted to show you how to calculate some of these values in Excel. What I did was I took the spreadsheet we had on the board last time, and I put it into Excel. First, let's get the mean of each of these columns. Actually, these three columns are quantitative, and these two columns are qualitative, so we can actually only find the mean of the three quantitative columns. So how can we do that? Excel calls the mean an average, which is fine because mean and average mean the same thing. So what Excel wants us to do is to type in an equal sign, and then type in the name of the value that we want to calculate. The value that we want to calculate is an average, so we type in average. Then we put a parentheses right there, a left parentheses, and we highlight the column that we want to calculate the average of, and then we put a closing parentheses right there, and then press enter, and it gives us the mean, meaning the average of this column of data. And if we want to get the mean of these other two columns, we can put the mouse right there at the bottom right corner and drag it across, and it actually automatically calculates the mean of this column and the mean of this column. Just to see what happens, we can try to drag it across and see if it can calculate the mean of these two columns. It's probably going to give us an NA. Right, it can't calculate the mean of a list of words. So you can't get the mean of a column of qualitative data. What about the median? We can get the median of these columns. Well, we can have a median of these first four columns. Remember, you can have a median for quantitative data or for ordinal data, but not for nominal data, which we have over here. So to get the median, we can type in equals, and then the word median. Put our left parentheses right there. Highlight the first column on the left. And then we put our closing parentheses and then press enter. And if we drag it across, it'll give us the medians of these two columns. Let's see if it can calculate the median of a column of ordinal data. First, let's just take a look at it to see what the median would be. If we put these in order, it would be freshman, sophomore, junior, senior. So the middle value would be sophomore, so median should be sophomore. Oh, okay, so Excel can't calculate the median of a column of ordinal data, so we can just type in the word sophomore, since that is the median. Now what about the mode? To get the mode of these columns of data, we can type in equals mode, and it has two choices. It says mode multiple or mode single, or just mode. I think we should probably just click mode right there and put our parentheses, highlight the column, and then press enter. I think I made a mistake. I typed in the wrong parentheses. We can drag it across to get the modes of these columns. I'm not sure if it can calculate the mode of a column of ordinal or nominal data. We'll drag it across and see what it does. No, it can't do it. What about the range? Well, I don't think Excel has a function that can get the range, so we might have to do it on our own. The highest value here is 40, and the lowest value is 18. So 40 minus 18 is 22. That's the range. Over here, the highest is 15 and the lowest is 12, so the range is 3. And over here, the highest is 2, the lowest is 0, so 2 minus 0 is 2. What about mean absolute deviation? Excel calls the mean absolute deviation the average deviation. So it's AVE-DEV. Type in the left parentheses. Drag it across, and the H column has more spread or more dispersion compared to these two columns. Notice how in this column the numbers are spread out all the way between 18 and 40, and over here in the number of units column the numbers are pretty similar. They all fall between 12 and 15, and over here the numbers are all pretty similar, meaning close together. They're all between 0 and 2. So the mean absolute deviation should be the highest right here, and it should be lower here and here, because it comes out to a higher number when the column has more spread. So yes, it did come out much smaller over here compared to when we calculated it with the H column. The same thing will happen with the variance and standard deviation, because they also measure the spread of the data. For variance, we have to type in equals VAR. See how it says VAR.P and VAR.S? One of these is the population formula, which doesn't have the n-1, and then the sample formula, which does have the n-1. Let's say that this data is from a sample, because it's a pretty small set of data, and most data sets that people collect are from samples. So we'll say that it's a sample and choose VAR.S. Let's highlight this column. Let's drag it across. So the variance did come out higher here and lower over here and here, because it comes out to the highest number when the data has the most spread. For standard deviation, we would type in equals STDEV.S. This is for sample. So it'll come out to the highest number here, and it'll come out to lower numbers over here because these columns are less spread out. Right, so that is what happened. And over here we could enter in the median and mode, and over here we could enter in just the mode because a set of nominal data has a mode only. So sophomore is the median. What's the mode down here? The mode is the value that shows up the most number of times. So Freshman shows up twice, the other values only show up once, so the mode is freshman. And what's the mode over here? It looks like each value only shows up once. Psychology, sociology, engineering, business, engineering. No, engineering shows up twice, and every other value shows up once, so the mode is engineering.
This is the same spreadsheet that we had in Excel. I showed you how to summarize a set of data with descriptive statistics. Now I want to show you how to summarize a set of data by creating tables and graphs. And the tables and graphs that I'm going to show you how to create in this video are meant to display something called frequencies. Now before we get into creating the tables and graphs, let's talk about what the word frequency means. The frequency of a value is the number of times the value appears in the data set. So let's look at the number of times 30 appears in the age column. 30 appears once in the age column, so the frequency of 30 is 1, because the age of 30 only appears once in the data set. Let's look at the number of units column and look at this value of 13 units. The value of 13 units actually shows up twice in the data set because we have two people who are taking 13 units. So we would say that this value has a frequency of 2, and it looks like two people are taking 12 units, so this value of 12 units would have a frequency of 2 because it shows up 2 times. So the frequency of a value is the number of times it appears inside its column of data. Now let's talk about how to display frequencies in a table or in a graph. And the way that we present the frequencies actually depends on what type of data we have. It depends on if it's quantitative or qualitative. If we have a column of qualitative data, we would present the frequencies in something called a bar graph. And let's create a bar graph for the grade level column. We need a line for the x-axis. So the values that appear in the grade level column are freshman, sophomore, junior, and senior. So we'll put those values down here. We'll put those words down here. I'll have to make the font smaller so it can fit. This is freshman. This is sophomore. Junior and senior. We need to have a y-axis that'll show the frequencies. We'll just put some tick marks on the y-axis. Now what's the frequency of freshman? Well, freshman appears twice. So what we would do is we would make a bar going up to 2 right here. And how many times does sophomore appear? Sophomore only appears once in this column of data, so since sophomore has a frequency of 1, it goes up to the first tick mark. This just shows that it appears 1 time. What about junior? We have one junior in the data set, so it has a frequency of 1. And senior also appears once, so it also goes up to the first tick mark. So we just created a bar graph of this column of data for grade level. What about for this other column right here, for college major? We could also create a bar graph for college majors. Whenever you have a column of qualitative or categorical data, you can create a bar graph. We'll talk about what to do when you have a column of qualitative. We'll talk about what you do when you have a column of quantitative data after we finish with these two columns of qualitative data. So let's put the values down here. And since it's a column of nominal data, the values don't have a clear order to them like they did over here. Since this was a column of ordinal data, it was clear what order we should put these values in.
What we'll have to do is just choose an order to put these values in. We can just follow the order from top to bottom. So we'll put psychology first, and then sociology, and then engineering, and then business. So let's find out what the frequency of psychology is. Psychology appears one time in this column, so its frequency is 1. So go up to the first tick mark. What about sociology? It also appears once. And engineering appears twice. So this will go up to the second tick mark. And then business appears once, so it goes up to the first tick mark. And we've created a bar graph for the grade level column and a bar graph for the college major column. And I said that you create a bar graph when you have a column of qualitative or categorical data. There's a different type of graph that you would make for a column of quantitative data. And it looks like the graph that you would make for a column of quantitative data looks like a bar graph, but it is actually a little bit different. And I'll show you why. The graph that we would make for a column of quantitative data is called a histogram instead of a bar graph. When you make a histogram, you start with a number line, like this, and then we would start with the lowest value right here, which is 0. We would mark off all of the different values that appear. The only values that appear are 0, 1, and 2. So we don't even need this extra part of the number line out here. We can just stop once we pass the highest value. And then we'll create a y-axis for the frequency. I should probably move 0 over a little bit just so it's not so close over here. So 0 has a frequency of 2 because 0 appears twice in this column. So this bar will go up to 2. And what about 1? Well, 1 appears once in this column, so it has a frequency of 1. So it goes up, this little bar will go up to the first tick mark. One difference between a histogram and a bar graph is that in a histogram, the bars touch each other. So this bar would actually be touching right here. And the frequency of 2 is 2 because 2 people have 2 children. This value appears twice in this column. So this bar will go up to 2. So one difference between a histogram and a bar graph is that in a histogram, the bars touch each other, and in a bar graph, they're separated from each other. And also in a histogram, you have numbers on the x-axis down here. And in a bar graph, you typically have words down here, or categories. So these two graphs would be called bar graphs. This one would be called a histogram. So this is a histogram for number of children. We can also make a histogram for number of units. I'll move this down a little bit so we can see that it's separated from this graph over here. We'll make a number line for number of units. The lowest number is 12 and the highest number is 15, so our tick marks will go from 12 to 15. What's the frequency of 12? 12 appears twice, so it has a frequency of 2. We'll go up to 2 right there. 13 shows up twice, so it has a frequency of 2. What about 14? 14 doesn't appear at all, so it has a frequency of 0, so we'll just leave this blank. What about 15? 15 appears once, so this will go up to the first tick mark. Whenever you have a value like this that has a frequency of 0, you just leave it blank. And we don't include any values that are below the lowest value or above the highest value. That's why we didn't include 11 and we didn't include 16. But when you have a value in between the highest and lowest values that has a frequency of 0, you just leave a gap in the histogram like we did here. So this is for number of units. I'll move these over so I have more room. Now let's make a histogram for age. Here we have a column of numbers where it's not very easy to make a histogram like we did here, where we just mark off all of the different whole numbers between the lowest and highest values. The reason why is because the values go all the way from 18 to 40, so it would be a very long graph if we marked off every number between 18 and 40. So what we can do instead is we can create groups of numbers. I'll show you what I mean. 18 is between 15 and 20. So maybe instead of just marking off 18, we could mark off 15 to 19. And then next we could mark off 20 to 24. So we're doing intervals of 5 numbers at a time. I'll move this over so we have a little bit more space. Next we would have 25 to 29. And then after that we would have 30 to 34. And then after that we would have 35 to 39. We'll keep going until we pass the highest value. Looks like the highest value is 40, so we need one more interval. Each of these groups is called an interval. The technical word is actually a class interval. We'll talk about that word more later. So we need one more class interval, which will be 40 to 44. And we don't have any values that are above that interval, so we can stop there. We don't have any numbers between 45 and 49. And we also don't have to go any lower than this because we don't have any numbers between 10 and 14 because 15 is the lowest number, so we can stop here. We don't have to go any lower than this interval. So now we have to count how many numbers appear between 15 and 19. In this column of data, in the age column, how many numbers are there that are between 15 and 19? Well, looks like only one number because 18 is the only number that's between 15 and 19 in this column. So this interval down here has a frequency of 1. It contains one number. So we'll go up to the first tick mark. Next we have to find out how many numbers are there in the age column between 20 and 24. Well, 21. Looks like 21 is the only number that's between 20 and 24. So there's 2 numbers that are between 20 and 24. So this goes up to the second tick mark. What about 25 to 29? We don't have any numbers between 25 and 29, so it has a frequency of 0. It'll just be a gap. And we have one number between 30 and 34, which is just 30. So this has a frequency of 1. We don't have any numbers between 35 and 39, but we do have one number between 40 and 44, which is just 40. So this will go up to the first tick mark, because if we have one number, then we go up to tick mark number 1. And people often talk about the shape of the histogram, or the shape of the bars in the histogram. I'll show you what I mean by the shape. If we outline the bars in each of these histograms with a curve, we'll see that each of these histograms has a certain shape. Let's do it with this first histogram right here. We'll outline the bars with this green curve. We can see that this one has kind of a wavy shape that has a curve that goes up and then goes down and then goes back up again, kind of like a camel. And this one has a shape where it goes up and it peaks at the left end, and it goes down, and then it goes up again, and then down again. This one would have this type of shape where it has a long flat area, then it goes up, it has another peak, and then it goes down and it's flat again, and then it has one more peak over here. And they've actually given names to the different types of shapes that can appear when you make a histogram. And next I'll go over what the different types of shapes are and what their names are. First, I wanted to remind you that these two graphs were called bar graphs because they were created with columns of qualitative data, and these three graphs were called histograms because they were created with columns of quantitative data. And each of these 5 columns of data has its own frequency graph. So age had its own graph, number of units had its own graph, and each of the other 3 columns had its own graph. So if you have 5 columns, you'll have 5 of these graphs. If we had 7 columns, we would have 7 graphs, and so on. One type of shape that you can have in a histogram is called a normal distribution. And a normal distribution is usually called a bell-shaped curve. A normal distribution and a bell-shaped curve have the same meaning, and in daily life you probably hear the word bell-shaped curve more often. I'll show you what that type of shape looks like. It just follows a bell like this. This is a normal distribution, meaning a bell-shaped curve. This is when the bars start off short at the left end, and then they gradually become taller, like this. Then they peak in the middle. And then they start to gradually trail off toward the right end. We can see that this normal distribution curve is just outlining the shape of the bars. So whenever you see a normal distribution curve or a bell-shaped curve, just realize that it's just outlining the shape of the bars in a histogram. Okay. In a normal distribution, the values that are near the center, meaning the more medium values, have the largest frequencies, and the values that are at the low end down here have lower frequencies, meaning they don't appear as often, and the values that are higher up here also have lower frequencies, and they don't appear as often. One type of variable that often follows a normal distribution is IQ. So when you're with IQ scores, most people fall into the middle range of IQ scores in here, and then fewer people are at the low end of IQ down here, and then fewer people are at the higher end of IQ up here. Height also tends to follow this type of a curve, where most people have medium heights in here. So heights between, let's say, 5 feet and 7 feet might have the tallest bars in here, and then there would be fewer people who were shorter than 5 feet tall, and fewer people who were taller than 7 feet tall, at least if you're talking about adults. So we know what a normal distribution is. Now what about a shape that doesn't follow a normal distribution. Next, we'll talk about the different types of non-normal shapes, meaning the shapes that don't follow a normal distribution. One possibility is to have a histogram that peaks further to the left than a normal distribution does. So you might have a shape like this that peaks near the left end, where the lower values appear more often and the higher values appear less and less often in the data set. So we can see that it peaks too far to the left to be a normal distribution. And this type of a shape would be called skewed to the right. And I'll tell you why it gets that name. It's actually either called skewed to the right or positively skewed. It involves the direction that the graph is trailing off toward. So we can see that the bars are trailing off toward the right end down here, meaning it peaks at the left end and then it gradually trails off and gets shorter when you go toward the right end. So just imagine this arrow going down to the right, and that's why it's called skewed to the right. And you can also think of it as it's trailing off toward the positive end of the number line, so it's positively skewed. Now what about the opposite type of graph? What if it peaks at the right end and then trails off to the left? The reason I'm putting a normal curve here is just to show you how it doesn't follow a normal curve. So when I draw this normal curve right here, this normal distribution, you can see how the shape of the bars doesn't follow this type of shape. So we'll make one that peaks at the right end like this. And then trails off toward the left end. If we make an arrow, we can see that it's trailing off toward the left end. So it's called skewed to the left, or negatively skewed, because you can imagine how it's trailing off toward the negative end of the number line. So it's negatively skewed. And you might be thinking that it should be the opposite, where it should be that if it peaks at the left end, it should be skewed to the left, and if it peaks at the right end, it should be skewed to the right. But it's actually not named that way. It's actually the opposite of what you would think it would be. The word skewed to the right actually refers to the direction it's trailing off toward. It doesn't refer to the side of the graph that it peaks at. So if it peaks at the left end and trails off to the right, it's skewed to the right. If it peaks at the right end and trails off to the left, it's skewed to the left. You might imagine if this was a mountain and you were stuck up here at the peak of the mountain up here, if you would rather walk down to the right, down the right side of the mountain, meaning if it would be easier to walk down this side of the mountain at the right end, then it's skewed to the right. And if you were stuck up here and this was a mountain, and if it was easier to walk down to the left end, then it's skewed to the left. There's two other types of non-normal shapes I wanted to talk about, meaning when I say non-normal, I just mean shapes that don't follow a normal distribution. You can also have a graph that peaks lower than the normal distribution and a graph that peaks higher than the normal distribution. And we'll talk about those next. I'll copy and paste the normal distribution down here. Just so we can have it to compare to these other graphs. Let's imagine a type of graph that's flattened out, kind of like a pancake, or more like a pancake, where maybe it's not perfectly flat, but it's more flattened out than a normal distribution is. Something like this. Maybe not like a pancake, but more like a butt cake. So we have a graph that's flattened out like this, and it peaks lower than the normal distribution. This more flattened type of shape would be called a negative kurtosis. It's kind of a strange word, but it's called a negative kurtosis. You can think of it as the word negative as meaning it peaks too low. So it might help you remember the name if you think negative means peaking lower than a normal distribution. If it peaks higher than a normal distribution, it's a positive kurtosis. What a positive kurtosis actually is when you have longer tails. I mean, the curve stays flatter longer, like this, and then it suddenly, or it more suddenly, becomes taller, like this. So instead of going up gradually, it stays flat longer, and then once you get closer to the center, it goes up more suddenly. And then it goes up higher than the normal distribution, so it might even go up this high. And then it goes down suddenly again, goes down pretty quickly, and then it becomes this flat tail down here. So we have these flat tails, and then we have this sort of sudden peak in the middle, this sudden tall peak in the middle. It's kind of like you're taking a normal distribution and squeezing it inward like this, where if this was a ball of dough, or like Play-Doh, I guess, if you pushed inward from the two sides, the peak would move in like this, and it would move up higher, and that would give you a positive kurtosis. Negative kurtosis would be like if you had a normal curve made out of Play-Doh and you pushed down on it to smash it down, and it became a flattened shape like this. It's just one way to think about it. So if it peaks lower than the normal curve, it's a negative kurtosis. And if it peaks higher than the normal curve, it's a positive kurtosis. And negative kurtosis is more flattened out like this. And in a negative kurtosis, the heights of the bars are more similar. We don't really have a peak that really stands out very much. But in a positive kurtosis, we have a peak that stands out a lot. The peak is more distinct than in a normal distribution because you actually have this tall and narrow peak that appears in the middle of right here in the graph. So actually, in a negative kurtosis, the peak of the graph is flatter and wider. See how this peak right here is flatter, both flatter and wider than the normal distribution. And in a positive kurtosis, the peak is narrower and taller than in the normal distribution. And there's one other type of shape that I could have covered, which is called a bimodal distribution, which is when you have a peak like this and then a second peak that goes up like this, where it actually peaks twice. So this one we call bimodal. And now I'll go through a PowerPoint slideshow, which will go through some of these concepts again. This PowerPoint slideshow is on frequency distributions. Frequency distribution is just a table or graph that can display frequencies. We talked about what the word frequency means. We'll go over it one more time. The frequency of a value is the number of times that a value appears in a set of data. So if I ask 8 people to tell me how many classes they're taking this quarter, and these were their 8 answers, then the frequency of 2 would be 3 because the answer of 2 appears 3 times. It's 1, 2, 3. The frequency of the value of 3 is 2 because 2 people said 3. There's 2 3s in the data. The frequency of 4 is 2 because there's 2 4s, and the frequency of 5 is 1 because there's 1 5 in our list of data right here. And there's different ways to present frequencies. And if you have a column of nominal data in a spreadsheet, you would create a bar graph to show the frequencies. If you had a column of ordinal data, such as a column of grade levels, you would also create a bar graph. And the categories on the x-axis would follow a specific order, such as freshman, sophomore, junior, senior. If you have a column of quantitative data, you would create either a frequency distribution table or a histogram. And we talked about what the word frequency means. It's the number of times that the value appears in the data. And this describes how to create a frequency distribution table. You have the x column that lists all of the different values that were found in the column of data. And then you have the frequency column, which says how many times each of the values appeared in the column of data. Here's another example of frequencies. Let's say we asked 10 people how many times they go to Starbucks each week, and these were their answers. Right here I'm showing you what the frequencies are. We have 4 1s, we have 2 2s, we have 3 3s, and we have 1 5. So that's why these are the different frequencies down here. Since 1 appears 4 times, 1 has a frequency of 4. Since 3 appears 3 times, then 3 has a frequency of 3, and the same thing is true for these two numbers over here. If we wanted to create a frequency distribution table for this set of data right here, it would look like this. Remember, these were the 4 answers that appeared in the list of numbers. We had 1s, 2s, 3s, and 5s. So this says 1, 2, 3, 5. And this just shows how many times each of those numbers appeared in a set of answers. And I talked about before how with some types of variables, like with age, there's too many possible values to list all of them on the x-axis. So it's better to create these groups that we see here, like 10 to 19, 20 to 29, and 30 to 39, and put those groups on the x-axis instead of every whole number. Each of those groups is called a class interval. So let's look at an example of a grouped frequency distribution table. We ask these 18 people their ages, and we get these we ask these 15 people their ages, and we get these 15 answers. This would be a grouped frequency distribution table. Each of these groups over here is called a class interval. So 20 to 29 is the first class interval, 30 to 39 is the second class interval, and this is the third class interval. So overall, we have 5 class intervals in this table right here. Because 1, 2, 3, 4, 5. So each group is called a class interval, and we have 5 of them. There's also a different term called the class width. The class width is the span between the lowest and highest numbers inside each of the class intervals. So the class width is how far these two numbers are apart from each other. The class width in this example is 10, because what the class width actually is the number of numbers between this low point here and this high point right here. So let's think about how many numbers there are between 20 and 29. It might seem like there's 9 numbers between 20 and 29, but there's actually 10. We can see that right here. There's 5 numbers between 20 and 25, and then 26 to 29 gives us 5 more numbers. Well, actually, I made a mistake because there's actually 5 numbers between 20 and 24, because it's 1, 2, 3, 4, 5. And there's 5 other numbers between 25 and 29. So there's 5 numbers between 20 and there's 5 numbers between 20 and 29. I think I made a mistake. Let's see, 1, 2, 3, 22, 23, 24, 26, 27, 28, 29. There should be 10 numbers between 20 and 29. So 20, 21, 22, 23, 24. Oh, I skipped over 25. Sorry. That was my mistake. So there are 10 numbers between 20 and 29. So which is why you would say that the class width is 10. because 1, 2, 3, 4, 5, 6, 7, 8, 9 gives you 9 numbers, and then when you include 20, that gives you a 10th number. So, and actually, if we did the same thing for each of these other intervals, we would get 10 numbers each time, because there's 10 numbers between 30 and 39, 10 numbers between 40 and 49, and so on. So each of these is each of these class intervals covers 10 numbers. They all have the same width, which is why you would just say that the class width in this histogram is 10. Actually, in every histogram, each class interval always has the same class width, because you couldn't create a histogram, for example, that would be 20 to 24, and then 25 to 59, and then 60 to 99, because that would, if you did that, you would have different class widths, and you're not allowed to have different class widths. Every class interval has to have the same class width. And what if instead of doing this, what if we had a different table in which the intervals were 0 to 49? I'll do an example right here. What if it was 0 to 49, and then 50 to 99, and then 100 to 149, and then 150 to 199. In this table, we have a class width of 50, because each of these 4 class intervals covers 50 numbers, because there's 50 numbers between 0 and 49. There's 50 numbers in here between 50 and 99. There's also 50 numbers in here and 50 numbers in here. So we would say class width is 50. And if we had this right here, the class width would be 10. Because each interval covers 10 numbers. There's actually a formula that can give you the class width. What you have to do is you have to just choose one of the intervals. It can be any of the intervals, and then take the high number of the interval, which is called the upper boundary of the interval, and subtract it by the low number of the interval, which is called the lower boundary, and then add 1. So each of these numbers is called a lower boundary. The lower number in each of these intervals is called the lower boundary. The upper number is called the upper boundary. So every interval has a lower boundary and an upper boundary. So let's use this formula right here. Class width equals upper boundary minus lower boundary plus 1. So So the upper boundary is 49. Minus the lower boundary of 0, which is right here, plus 1 at the end. So what's 49 minus 0 plus 1? 49 minus 0 is just 49. And then 49 plus 1 is 50. So we get our class width of 50. Let's do the same thing down here for the class width of 10. Here we have our lower boundary. Here we have the upper boundary. You take the upper boundary of 9, subtract it by the lower boundary of 0, and then add 1 at the end. 9 minus 0 is 9, and then 9 plus 1 is 10. So we get our class width of 10 using this formula. One thing you have to remember is that the class width and class interval are two different things. That's one thing that confuses a lot of people on a multiple choice test is the difference between a class interval and a class the difference between a class interval and a class width. So if you're taking an exam, it's a good idea to make sure that you remember the difference between those two concepts. This just covers some guidelines that are commonly used about how many intervals to use and what type of class width to use. It's usually better to use a nice number for the class width, like 5 or 10, like a multiple of 5 or a multiple of 10. So maybe 5, 10, or 20, or 50, or 100. Because if you use a class width like 7, it might look a little bit strange because then your intervals would be 10 to 16, 17 to 23. This is with a class width of 7, and then 24 to 30. It doesn't look as nice, and it's not as easy to follow or to interpret. So it's better to use multiples of 5 or 10 for class widths. Also, all of the intervals need to have the same class width. So you wouldn't be allowed to make a table like this where you have 10 to 19 as the first interval and then 20 to 49 as the next interval and then 50 to 99 as the next one. This wouldn't be allowed because the intervals have different widths, and the rule is that all intervals have to have the same class width, so this is not allowed. So we talked about histograms. In a histogram, each of the frequencies that were in that F column is shown as a bar. This is a histogram of those 15 heights that we saw on another slide. It's a histogram of this table right here. Well, we started with this data, these 15 heights. We made them into a frequency table, and then now I'm taking this table and making it into a histogram. So notice how this bar of 2 right here, this first blue bar, that's just this frequency of 2 right there, and then notice how we have 6 and then 2 next, and then 4 and then 1. So 2, 6, 2, 4, 1. Here we just have 2, 6, 2, 4, 1. So it's the same information just presented in a different way. And like I said, the histogram makes the shape more obvious. So we can see here that we have a shape where the histogram goes up, down, up, and then down again. Here's another example of a set of data where 20 people are telling us their heights. We get this table right here. This is the table of our answers. And then if we make this into a histogram, we get this type of shape right here. This type of shape would be called a normal distribution, or a bell-shaped curve. And it's not perfectly normal, but I just did the best I could to make a histogram that looks pretty close to a normal distribution. Notice how when you have a normal distribution, most people are in the middle. So see how we have 12 people who are between 5 feet and 6 feet tall. So most people are at the middle of height. Most people have medium heights, and we have fewer and fewer shorter people down here, and fewer taller people down here. We have very few people shorter than 4 feet down here, and very few people taller than 7 feet. So this normal distribution is actually a pretty realistic type of shape for height. Height would usually follow this type of shape in real life. And this is just outlining the histogram with this bell-shaped curve. This normal distribution. Like I said, if it peaks at the left end, it's skewed to the right. If it peaks at the left end and trails off to the right, it's skewed to the right. I was trying to think of an example of something that would follow this type of shape. And I was thinking about fast food employees, such as people who work at McDonald's or Burger King. In a fast food company, you have a lot of cashiers who make a few dollars per hour, maybe, I'm not sure what it is now, maybe $8 per hour or $7 per hour. So let's think about the incomes of fast food employees. In a fast food company, you have a lot of cashiers who have lower incomes. The cashiers probably have the lowest incomes of all people at the company. So they're at the low end down here because they're at the left end because they have the lowest incomes, and they have the tallest bar because there's a lot of them. Further toward the right, we have maybe the assistant managers who make more money than the cashiers, or maybe a little bit more money. Since they make more money, they're further to the right than the cashiers are. But since there's fewer assistant managers than cashiers, so that's why their bar is shorter. And if we go further to the right, we maybe have managers who make more money, but there's fewer of them than the assistant managers, so their bar is shorter. And then I'm not sure what these people would be. Maybe a higher level manager who makes more money, but there's even fewer of them. And then up here we have, it looks like one person because this bar goes up to 1. This would probably be the CEO of the company, and this person makes the most money, so they're furthest to the right. But there's only one CEO, so the bar is very short. So the incomes of fast food employees probably follows this type of shape. And my first job was working at Burger King, so I was actually one of these people down here in this bar down here. I was one of the cashiers who makes the lowest amount of money. That was my first job when I was in high school. And you can see the shape which is skewed to the right. So whenever something is skewed to the right, you have a lot of people with lower numbers and fewer people with larger numbers. In my example, it was talking about how in a fast food company, you have a lot of people with lower incomes down here, such as cashiers and assistant managers, and you have fewer people up here who make more money, So what about something that would be skewed to the left? The example I was thinking about was maybe people who work at a hospital. I'm not totally sure if that would be correct, but I'm just thinking that that could be skewed to the left because let's think about the incomes of people who work in a hospital. You have a lot of doctors and physicians and who make a lot of money. So those doctors and physicians are down at the right end because they make a lot of money. They have higher incomes. And there's a lot of them in the hospital, so they have a tall bar. And then when we move down here toward the lower incomes on the number line, we might have nurses who might make a little bit less money. And then down here, we might have the support staff of the hospital, such as receptionists or maintenance workers who make less money. So they're down toward the left end of the income number line. And I'm thinking that there might be fewer of those maintenance workers compared to the doctors over here, so their bars would be shorter. So it could be that the incomes of hospital workers follow this type of shape. Here's another example that's commonly used for skew to the left and skew to the right. If a classroom full of students takes a difficult test, you have, if you make a histogram of the exam scores, then you have a lot of people who are getting lower scores down here because a lot of people did poorly. You maybe have a lot of people with B's and F's down here, which is why the bar is so tall. And then fewer and fewer people are getting these higher grades up here. So you have fewer C's, fewer B's, and even fewer A's if the test is difficult. If the test is easy, then students' grades will follow the other shape, which is skewed to the left. If the test is easy, then a lot of the students in the class will get the high grades down here. I mean, a lot of the students will get A's, which is why this bar at the right end is so tall. Actually, this is B's, but a B is still a pretty good grade. So we have a lot of students getting B's right here. We have fewer C's, fewer D's, and even fewer F's. Very few people are failing down here. So if the test is easy, then the students' grades will be skewed to the left. This is just talking about the mean, median, and mode of the data. We'll talk about this right here. Well, if the column of data is skewed to the left, the mean will be a larger number than the median, meaning the mean will be to the right of the median. If the data is skewed to the left, like this, then the mean will be a lower number than the median, meaning the mean will be on the left side of the median. So you can just think of it as the mean being pulled in the direction of the skewness. If it's skewed to the right, the mean is pulled toward the right end. And then the mean is to the right of the median. If the data is skewed to the left, then the mean is pulled toward the left end, and the mean is on the left side of the median. I think that's a good way to remember it. If the column of data follows a normal distribution, then the mean and median are both the same number. Actually, if the data follows a normal distribution, the mean, median, and mode are all the same number. We talked about kurtosis, which involves the amount of peakness in the histogram. If the histogram has a shorter and wider peak than a normal distribution, meaning if the shape is flatter than a normal distribution, then that column of data has a negative kurtosis. If the column of data has a taller and narrower peak than a normal distribution, then that column of data has a positive kurtosis. Here's, I think this is a good picture right here. I got this from a website. This blue line is a negative kurtosis. This red line right here is a normal distribution, and this green line here is a positive kurtosis. I was trying to think of an example of a variable that might have a negative kurtosis and a variable that might have a positive kurtosis. I was thinking that the ages of people living in a city might have a negative kurtosis. So, for example, the ages of people living in San Jose might have a negative kurtosis, or the ages of people living in any city. If you think about it, all of the ages probably have frequencies that are about equal to each other. What I mean is, if we made a bar for each of the ages, then the bars would probably be about the same height, meaning the graph would probably be pretty flattened out. I'm not exactly sure what the bars would look like, but I'll just make out some bars. Remember that this bar would show the number of people in the city who were in their 20s. This bar would show the number of people in the city in their 30s. And this would be the number of people in their 40s, and this would be the number of people in the city in their 50s. So there should be the number of people in each age group should be about equal, because I don't think there would be a reason for one age group to show up a lot more than another age group. So the number of people in the 20s, the number of people in the 30s, the number of people in the 40s, and the number of people in the 50s should be about equal numbers. I wouldn't really expect that there be a peak like this. For example, I wouldn't imagine one age group really standing out. Like, it would seem strange for there to be a small number of people in their 20s, a large number of people in their 30s, and only a few people in their 40s. So I wouldn't imagine it being something like this, where one age group shows up a lot more than other age groups. I would imagine it being something more flattened out like this, where each age group um, has about the same number of people. So I was thinking of age as maybe having a negative kurtosis. What about something with a positive kurtosis? I was thinking about maybe the number of hours that people sleep at night. So you probably don't have very many people who get very low amounts of sleep like this. And once you get to about 5 hours, you might start to have some more people. And I'm thinking that most people probably get somewhere between 6 and 8 hours. So these bars would be really tall. Once you get past 5 hours, the histogram should go up pretty suddenly, like this. And then you probably have a lot of people between 5 and 8 hours. But then after 8 hours, I'm thinking it would come down pretty quickly, where there wouldn't be very many people sleeping 9 hours, and there would be very few people getting more than 9 hours. So it would go back down again very quickly. So I'm thinking that there would be a lot of people concentrated in this narrow area of the number line between 6 and 8 hours. So I'm thinking you would have a lot of people piling up between 6 and 8 hours with a tall peak, and very few people below 6 and very few people above 8, which would give you a positive kurtosis. So I was just thinking that maybe age would have a negative kurtosis and maybe sleep would have a positive kurtosis, but I'm not completely sure if that's correct because I haven't looked at any data on these two things. Let's go back to this slide again. The reason why I put the normal distribution in between the negative skewness and the positive skewness, and in between the negative and positive kurtosis, is because a normal distribution is halfway between a negative skewness and a positive skewness, and it's halfway between a negative kurtosis and a positive kurtosis, because here we have a peak at the right end, here we have a peak in the middle, and here we have a peak at the left end, and here we have a peak that's low, here we have a peak that's high, and here we have a peak that's somewhere in the middle. So actually you would say that a normal distribution has no skewness and no kurtosis. So a normal distribution is actually the absence of skewness and kurtosis. A normal distribution has both no skewness and no kurtosis. And there's a value that can actually be calculated with a formula to measure the amount of skewness or the amount of kurtosis in a set of data. And we won't go over the formula for skewness and kurtosis, but we'll talk about what the value shows. If the data is perfectly normal, then the skewness value will be 0. So let's say that this number line right here is the skewness value. Let's move this down. perfectly normal distribution will have a skewness value of 0. As the skewness value gets further toward the left, it means that the data has more of a negative skewness. So down here and down here, it would mean that if the value comes out somewhere down here, it means that the data is starting to look more like this, like a negative skewness. And if the value is coming out somewhere up here, above 0, it means that the data is starting to look like a positive skewness. So it's pretty straightforward, because if the skewness value comes out to a negative number below 0, it means that the data has a negative skewness. And if the skewness value comes out to a positive number above 0, it means that the data has a positive skewness. And the further the skewness value comes out below 0, the more extreme of a negative skewness you have, or the more dramatic of a negative skewness you have. And the further the skewness value comes out above 0, the more dramatic of a positive skewness you have. And so if the data looks pretty normal, but maybe has a little bit of a negative skewness, then you might get a value close to 0, but a little bit lower than 0, like maybe right here. So right here might be a slight negative skewness. If the data is pretty close to normal but has a little bit of a positive skewness, you would get a value a little bit above 0. And actually, kurtosis works the same way. If the data is perfectly normal, then it'll have a skewness value of, it'll have a kurtosis value of 0. If the kurtosis value comes out to a negative number, then you have a negative kurtosis. If the kurtosis value comes out to a positive number, your data has a positive kurtosis. And the further the kurtosis value is below 0, the more dramatic of a negative kurtosis you have. And the further the kurtosis value is above 0 out here, the more dramatic of a positive kurtosis you have. So right here could be a slight negative kurtosis, and right here could be a slight positive kurtosis. So a perfectly normal distribution will have a skewness value of 0 and a kurtosis value of 0. And actually, if the skewness value and kurtosis value are both between -1 and +1, then you could say that the data is at least close to normal. That's the guideline that's used. If the skewness and kurtosis values both fall between -1 and +1, the data is at least close to a normal distribution. Because anything between -1 and +1 is roughly no skewness, and down here anything between -1 and +1 is roughly no kurtosis. So if it has roughly no skewness and roughly no kurtosis, it's close to normal. Let's take a look at what types of shapes we see right here in these histograms that we created earlier. Looks like this one is skewed to the, maybe skewed to the right, because it peaks at the left end and trails off, because this bar down here is shorter than these two bars over here. So it might be a little bit of a positive skewness. This one over here looks like a positive skewness also, because it peaks at the left end and it trails off toward the right with shorter bars down here. This one right here doesn't look like it really has much of a skewness. It's more bimodal. And I'm thinking that all of these probably have more of a negative kurtosis, because They all look pretty flattened out. We don't really have any tall bars that really stand out in any of these histograms. So let's calculate the skewness and kurtosis values to see what they come out to. We can calculate them with Excel. We just have to go back to this spreadsheet right here. Remember, I calculated the mean, median, and mode, and the measures of dispersion. I can also calculate skewness and kurtosis values for all of the quantitative columns. The qualitative columns don't have skewness and kurtosis. So what I can do here is I can type in equals skew, type in SKEW, then I highlight the age column, I close the parentheses, and I get the skewness of the age column, and it's 1.15, which is a positive skewness. I predicted it would be a positive skewness because find it again. Oh, because the age column, the data peaks at the left end and it trails off to the right. So this data right here for age had a skewness value of 1.15. So since the shape had a positive skewness, the skewness value came out to a positive number. We can also find the skewness value for number of units. It's also a positive number, which means that the number of units column has a positive skewness. Let's look back to see what the data looks like. I said that number of units looks like it has a positive skewness because it trails off toward the right end. What about number of children? I said that it looks like number of children doesn't really have a skewness. So I'm thinking that the skewness value should come out close to 0 for number of children. Right, so it actually does have a skewness value of 0. It has no skewness at all. And what about kurtosis? I said that all three of those histograms were pretty flattened out, so I was thinking that they would all have more of a negative kurtosis. So let's see if these kurtosis values come out to negative numbers. I type in equals KURT for kurtosis. So it's actually, well, it's close to 0. It's actually slightly positive for the age column. Number of units actually has a high positive kurtosis, and number of children has a pretty low negative kurtosis. So this is actually a pretty dramatic positive kurtosis, and this is actually a pretty dramatic negative kurtosis. So let me look back at those two histograms to double check their shapes. So number of units positive, number of children negative. Number of units. Well, number of children does look kind of flattened out, so that's why it has that value of -3 for kurtosis, and it says that number of units has a positive kurtosis of +2, and it's hard for me to really imagine why, but I guess it maybe it's because it goes down here to 0 and then goes up pretty suddenly, so it has kind of a sudden peak right here. That's maybe why it has that positive kurtosis of +2. Remember, this was a kurtosis of -3, and this was a kurtosis of +2. I drew these pictures just to make one last point. These actually aren't histograms of actual data. I just drew these pictures. And I drew these to show that you can actually have different combinations of skewness and kurtosis. For example, this one right here looks like it has a positive skewness and a positive kurtosis because, well, it peaks at the left end and it trails off to the right, which means it has a positive skewness. And it also has this tall and narrow peak, which means it has a positive kurtosis. This one looks like more of a positive skewness and a negative kurtosis because it peaks at the left end and trails off to the right, so it has a positive skewness, but it's flattened out, which means it has a negative kurtosis. This one over here looks like a combination of a negative skewness and a positive kurtosis. It has a negative skewness because it trails off toward the left end, and it has a positive kurtosis because it has a tall and narrow peak, just like this graph over here. This one right here would be a combination of a negative skewness and a negative kurtosis because it has a negative skewness because it peaks at the left and trails off to the right, just like it did up here, but it's flattened out, which means it has a negative kurtosis. So over here we have positive kurtosis, positive skewness and positive kurtosis. Since it trails off to the right, so it has a positive skewness, and it has a tall and narrow peak, so it has a positive kurtosis. This one is a positive skewness, and a negative kurtosis. It has a positive skewness because it peaks at the left and trails off to the right, just like this graph did. But it has a negative kurtosis because it's flattened out. This one over here has a negative skewness and a positive kurtosis. It has a negative skewness because it peaks at the right end and it trails off toward the left. That's why it has a negative skewness. And it has a positive kurtosis because it has this tall and narrow peak. This one down here would be a negative skewness and a negative kurtosis. It has a negative skewness because it peaks at the right end and trails off to the left, just like this graph did. But it has a negative kurtosis because it's flattened out.